Preparing for a big technical interview, especially for something like the CompTIA Network Plus, can be pretty nerve-wracking. You're always wondering, what are they actually going to ask? So today we're going to run through some of the core concepts you'll almost certainly encounter, sort of a rapid-fire prep session.
I love this idea. Getting these fundamentals locked down is all about building confidence before you walk into that room.
Let's start with the absolute bedrock of network understanding. The OSI model, or Open System Interconnection Model, is a conceptual framework that breaks down network communication into 7 distinct layers, from the physical connection all the way up to the application you're using. This model is crucial because it provides a universal language for professionals to manage, troubleshoot, and build networks effectively.
Exactly. It's like having a standardized blueprint for every network interaction. Without it, diagnosing a problem would be like trying to fix a car with no idea where the engine parts are supposed to be.
So when we talk about troubleshooting a network issue, say slow internet, how does understanding these 7 layers actually help pinpoint the problem?
It allows us to isolate the issue. If the physical layer is down, no data is moving. If it's a transport layer issue, it might be about how data is being delivered reliably. Each layer gives us a specific area to investigate, making complex problems manageable.
That makes perfect sense. So the OSI model gives us a structured way to think about how data moves. And speaking of data movement, a key part of that is assigning addresses. How do we manage IP addresses to ensure devices can communicate and networks are optimized?
That brings us to subnet masks. A subnet mask is a 32-bit number that essentially masks an IP address, dividing it into 2 key parts: the network address and the host address. This segregation is fundamental for optimizing how a network performs and making it easier to manage.
Right. It's how we segment a larger network into smaller, more manageable pieces. Think of it like assigning an area code and then a local number for a phone. The subnet mask tells you which area code the IP address belongs to, and then which specific phone within that area.
So, subnet masks help us organize and optimize. Now, when data travels across these networks, it needs a reliable way to get there. This brings us to transport layer protocols. What's the fundamental difference between TCP and UDP?
At the transport layer, we have 2 primary protocols, TCP and UDP. TCP, or Transmission Control Protocol, establishes a connection and ensures data arrives reliably and in sequence, which is why it's used for things like web browsing. UDP, or User Datagram Protocol, doesn't guarantee sequence or reliability, making it much quicker and perfect for real-time applications like online gaming or streaming.
It's the classic trade-off, reliability versus speed. If you absolutely need every single packet to arrive perfectly, like when loading a web page, you use TCP. If you can tolerate a dropped packet here and there for a smoother, faster experience, like in a video call, UDP is your go-to.
That trade-off is critical. Now, to manage traffic more granularly within a network, we can use something called a VLAN. What exactly is a VLAN, and what are its main benefits?
A VLAN, or Virtual Local Area Network, is a way to logically segment a physical network. It allows you to group devices together as if they were on the same LAN, even if they're in different physical locations. The main benefits are better security, improved performance management, and more efficient use of bandwidth.
Think of it like creating dedicated virtual highways within a busy city road system. You can separate different types of traffic, say sales team data from IT department data, so they don't interfere with each other, making everything run smoother and more securely.
That's a great analogy. So, VLANs help organize traffic internally, but what about protecting the network from the outside? That's where concepts like NAT and DMZs come in. Let's tackle NAT first. What does network address translation do, and why is it so significant?
Network address translation, or NAT, is a process that modifies the IP address information in packet headers as they travel across a router. It's significant because it helps conserve public IP addresses, a limited resource, by allowing many internal devices to share one public IP, and it also enhances privacy by masking internal network addresses.
Essentially, NAT acts as a gatekeeper and a translator for IP addresses. It lets all your devices on your home network use private IP addresses, but when they need to talk to the internet, NAT translates those private IPs into a single public IP that your router has. It's crucial for managing the scarcity of IPv4 addresses.
A critical function for managing IP scarcity. Now, speaking of devices connecting within a network segment, how does a switch differ from a hub, and why does that distinction matter?
When connecting devices within a network, we often use switches or hubs. A switch is intelligent. It recognizes the MAC address of each device and directs data only to the intended recipient, saving network resources and enhancing privacy. A hub, however, simply relays data packets to all devices connected to it, which can cause collisions and inefficiency.
Exactly. A switch is like a mail sorter who knows exactly which mailbox to deliver to, while a hub is like someone shouting a message down a crowded hall, hoping the right person hears it. Switches are fundamental to modern, efficient networks.
That analogy perfectly captures the difference. So, switches are smarter. Now, to further secure our networks, especially when connecting to the public internet, concepts like DMZs and firewalls are essential. What are the main advantages of setting up a DMZ?
A DMZ, or demilitarized zone, is an extra security layer that isolates your internal corporate network from untrusted external networks like the internet. By exposing only external-facing services, it protects your sensitive internal systems from direct threats.
It's like a secure lobby for your building. Visitors can access the lobby and maybe a reception desk, but they can't just walk into the main offices. The DMZ is that controlled buffer zone, preventing direct access to your most critical assets.
Crucial buffer, and firewalls are the gatekeepers for that buffer. Why are firewalls so critical in network security?
Firewalls are absolutely critical because they act as a shield, protecting an internal network from unauthorized external access. They monitor and control both incoming and outgoing network traffic according to specific security rules, blocking any data packets that don't meet those criteria.
They are the first line of defense. Imagine a security guard at the entrance of a building, checking IDs and deciding who gets in and who doesn't. Firewalls do that for network traffic, enforcing the security policies you've set.
A vital security guard. Now, beyond just blocking threats, we also need to detect and prevent them. What are IDS and IPS, and how do they differ?
IDS, or Intrusion Detection System, monitors network traffic for suspicious activity and alerts administrators. IPS, or Intrusion Prevention System, goes a step further. It not only detects threats, but also takes action to block or stop the intrusion in progress.
So, an IDS is like a security camera system that records suspicious behavior, while an IPS is like a guard who not only sees the suspicious activity but also intervenes to stop it. IPS offers a more active, immediate layer of protection.
That distinction is important for understanding the depth of security. To effectively manage all these systems and ensure smooth operation, network monitoring tools are indispensable. What are some of the most well-known network monitoring tools?
To keep networks running smoothly, we rely on monitoring tools. Some of the most popular include Wireshark for analyzing data packets, SolarWinds for overall performance monitoring, Nagios for infrastructure health, and PRTG Network Monitor for real-time data like bandwidth usage and packet loss.
These are the network administrator's eyes and ears. Wireshark, for instance, is like a microscope for network traffic, letting you see exactly what's going in and out. Tools like SolarWinds and PRTG give you the big picture, alerting you before a small issue becomes a major outage.
Indispensable for visibility. Now, to ensure devices can communicate easily, we need efficient IP address assignment. What is the function of DHCP in a network?
DHCP, or Dynamic Host Configuration Protocol, is crucial for making network setup easy. It automatically assigns IP addresses and other network settings to devices, which helps them communicate efficiently without manual configuration and prevents IP address conflicts.
It's the ultimate convenience for network administrators. Instead of manually assigning an IP to every single device, DHCP handles it automatically. It's like a hotel check-in desk that assigns you a room number as soon as you arrive, ensuring no two guests get the same room.
A huge time saver and conflict preventer. Now, when we need to quickly check if a device is reachable, there's a common command line tool. What does the term ping mean in network management?
When we need to quickly test if a device is reachable on the network, we use ping. This command sends an ICMP echo request message to a target and waits for an echo reply. A successful reply confirms that the device is online and accessible.
It's the network equivalent of knocking on a door to see if anyone's home. If you get a reply, you know the connection is working at a basic level. It's one of the first things an IT professional will do when troubleshooting a connectivity issue.
A simple but powerful test. Now, while ping tests reachability, another system translates human-readable names into those numerical IP addresses. What is DNS, and what role does it play in network operations?
DNS, or Domain Name System, is essentially the Internet's address book. Its job is to translate easy-to-remember domain names, like google.com, into the numerical IP addresses that computers actually use to find each other on the network.
Without DNS, we'd have to memorize IP addresses for every website we visit, which would be impossible. DNS makes the internet navigable for humans by providing that critical translation layer.
Absolutely essential for usability. Now, when we talk about how much data can be transferred, two terms often come up: bandwidth and throughput. What do they indicate in a network?
Bandwidth and throughput both describe data transfer rates, but they're different. Bandwidth is the maximum data transfer rate a network can handle, its potential capacity. Throughput is the actual rate of successful data transfer you experience, which is usually less than bandwidth due to factors like congestion.
Think of bandwidth as the width of a highway, and throughput as the actual number of cars that can pass a point per hour. You might have a wide highway, but if there's a traffic jam, fewer cars will get through than the highway's maximum capacity.
A clear distinction for understanding performance. Finally, let's touch on how networks segment traffic to avoid issues. What are collision domains and broadcast domains?
Collision domains are areas on a network where signals can interfere, potentially delaying data. Devices like switches and routers help segregate these to prevent delays. A broadcast domain is a network segment where a broadcast packet goes to all devices. Routers and VLANs limit these to manage traffic.
So, collision domains are about preventing devices from talking over each other in shared transmission spaces, which switches handle. Broadcast domains are about controlling how widely a message is sent out. Routers and VLANs act as barriers to keep those broadcasts contained. Both are key to efficient network design.
Excellent. So, if we were to wrap this all up, what are the absolute must-know takeaways from our rapid-fire session today?
Okay, let's try. First, know the OSI model as your foundational map. Then, understand that TCP is for reliability, while UDP is for speed. On the hardware side, remember switches are smart because they use MAC addresses, while hubs are not. And to manage traffic, you use VLANs for logical separation. For security, your firewall is the gatekeeper, a DMZ is your buffer zone, and an IPS is more proactive than an IDS because it takes action. And finally, don't forget the services that make it all work. DHCP hands out IP addresses automatically, and DNS is the internet's phone book. If you have those concepts down, you're in a great spot.